An electric field is a description of the space surrounding things that have charge. Now, it's similar to gravitational fields. It seems like the Earth reaches out and grabs and pulls the moon directly, but it doesn't. The presence of Earth's mass warps the space around it, and it's the space that puts force on other masses. So it's a gravitational field is a description of the space surrounding the Earth. And the property of a gravitational field is that space will now put force on things that have mass. And an electric field is also a property of space, is that space is warped in a different way than gravity warps space. But the property, an electric field is the property of space. That property is that space will now put a force on a charge. And maybe now is a good time to go ahead and define how strong the electric field is. Electric field is defined as how much force it will put on a particular charge. So an electric field is, the units of that would be newtons per coulomb. How many newtons of force space would put on a coulomb of charge. Now, if I had a whole bunch of electrons here, so there's a big negative charge right there, it would be that all of these would have to be so small it would be considered a single point. But the gravitational field does diminish as an inverse square law, that if we're out at this distance and feel some force on a charge, if you go twice that distance, the force would become 1/4 as much, 3 times 1/9, 4 times 1/16. But we could describe the space around that as a vector field map. So these arrows here are vectors, the length of the arrow representing the magnitude, how much force, and then of course where it's pointing would be the direction. So these vectors could be used to describe the space surrounding all that charge. And what it's showing is that if I put a positive charge here, there's a really long vector pointing in that direction, which means there's going to be a large amount of force pointing that way. And if I put a positive charge here, it's showing that there's going to be a little bit of force in that direction. Now, there's limitations to the effectiveness or the ability to be able to describe the space with vectors. The reason is, however long this vector is here, this vector should be drawn 16 times as long. And that's because out at 4 times the distance, it would be 1/16 as much. And the vectors start to overlap, and it gets to be a little convoluted. So the better way to, or maybe just another way of describing the space around all this charge is not in terms of a vector field map, where there's a variety of vectors drawn at different locations, but rather we draw it as electric field lines. Now, these lines here do have arrows on it, but they are not vector quantities. The length of that line does not represent magnitude. It is just representing the direction of the field at any point. Now, we can look at this picture and determine magnitude, like how much force there would be at a particular spot. And that's going to be how close the lines are together. So this is an electric field line. Here is another electric field line in very close proximity. And the closer those lines are together is what represents the strength of the electric field. Out here, you put a positive charge here. These field lines are not nearly as close together. So the force in that direction, or the field in that direction, is going to be a lot smaller. And now maybe is a good time to say that I guess I've maybe already said it, that the strength of the electric field is going to be proportional to the number of field lines in a given area. So how many of these lines pass through a certain area is going to be proportional to how strong the electric field is. And there is a convention that we need to learn, and it's maybe we should remember that a convention is there's lots of different ways we could have done something, but we all want to agree to do it the same way, and for that reason that becomes the correct way. Just we've all agreed to do it this way. So the convention is field lines are drawn in the direction of the force that would be put onto a positive test charge. So the key word here is that the force is going to be in the same direction as the force on a positive charge. So if I had a positive charge here and I want to figure out what the electric field surrounding all that charge is, well, these are opposite charges, so they're attracted. That charge would experience a force in that direction, so the field at that spot would be in that direction. And if I put a positive charge over here, it would experience a force that way. Positive charge there would be experience a force that way. So because the convention is the field, these white lines, is drawn in the same direction as the force that would be put onto a positive charge. Okay, so here the field is in the same direction as the force. If you put a positive charge over here, the same thing would happen. All right, let's look at the electric field surrounding a bunch of positive charge. Well, same thing. If I put a positive test charge out here, because these are opposite charges, they're going to repel. So the force on that charge would be away from it. So the electric field around this point charge, all these charges so small it takes up this space of about a single point, would be pointing away from all that positive charge. So if I had a negative charge, an electron, and it is experiencing a force in this direction due to an unknown field or an unknown charge, what would be the direction of the field surrounding that unknown charge? Now, you might be tempted to say the field was in toward it, but remember the field is in the same direction as the force put onto a positive charge. Here I had a negative charge. So if a negative charge experiences a force in that direction, if I had put a positive charge, it would have experienced a force in the exact opposite direction. So the field must have been pointing away from it. Again, the convention is that the field is drawn in the same direction as the force that would be put onto a positive charge, not a negative charge. If that was a positive charge, it would have experienced a force in that direction, which, because the negative charge was attracted to our unknown, it must have been positive. And electric fields go away from positive. They go toward negative. So this is just a description of this. This would be a single point charge. And if that is a negative charge, the field would be coming toward it. Positive charges would be attracted with force that way. If this was a positive charge, the field would be going away from it. And that's because a positive charge would be pushed that way. A positive charge over here would be pushed that way. Now, if we had two charges, here we can see the field lines are kind of arcing around and coming, kind of cooperating with each other. So if this is a positive charge, we want to figure out what this is. Well, it kind of looks like the field lines are going, we know the field lines are going out away from the positive, and they do look like they curve back around. So if they come out this direction, they're going to come in this direction, and that's why that must have been a negative. We can understand that a little bit more deeply here by going back to the definition of what an electric field is that it's a description of the space and space puts a force on other charges. So if I had a positive charge here, now these circles here are just representing equidistance, the same distance here as it is to there. So at this distance here, there's a large amount of force in that direction. So the field is very strong off in that direction. Here, the field is very strong off in that direction. At 2 radii, twice the distance, the force is going to be a fourth as much, and here a fourth as much, and there a fourth as much. At 3 radii, it's 1/9 as much. At 4 radii, it's 1/16 as much. But this is kind of drawing it as a vector field map, not electric field lines. If I had a negative charge over here, and I did the same thing, where I looked at how much field there was just due to that, here, there, and there, I would get all these vectors. So this negative charge would have a large force in that direction. Out at this distance, 1/4 as much, and 1/4 as much, and 1/4 and 1/4, 1/9, 1/9, 1/9, 1/16, 1/16. And then what we're doing is we're looking at the resultant electric field between these two charges. Well, because electric field is how much force there is per charge, right here in this spot in space, there was a force in that direction due to the positive charge. There'd be a force in that direction due to the negative charge. So we can add those two vectors and find the resultant. And that's what I'm doing all along the way here, that these two forces resulted in this one. These two forces resulted in that one. And what happens here is we can see that there's going to be this big force off in this direction, and then over here it kind of curves off in that direction. Over here it's pointing straight that way, fairly weak. Here it's coming back here. But if I were to do this for a variety of different locations in that space, the electric field would just be the resultant of those forces, and it would just curve back around like that, and curve up and all the way around like that. And that's if those are opposite charges. If they're like charges, this in this picture, this positive charge was a stronger, it's not just a single proton here. It's representing a positive charge that's larger in magnitude than this charge here. And again, we're coming back to what field lines show us, that if I had a positive charge right here, these field lines are very close together. And remember, it's the number of field lines in a given area that tells us the strength of the electric field. So a positive charge here would experience a pretty big force off in that direction. A positive charge right here, these fields are a lot further apart. These field lines are further apart, so it wouldn't experience as large of a force. If I put a negative charge here, well, these positive charges were pushed away, but a negative charge would be attracted, and the spacing between the lines right here is somewhere between here and here. So the electric field would be somewhere between in strength of those other two. Here we have like a plate, like a metal circular flat surface. And same thing here. If I had a bunch of positive charge there and a bunch of negative charge there, the electric field will go from the positive to the negative. And if we kind of look at the description there, it looks like all these field lines are going kind of straight between here and here. They do bulge out at the ends, but in between here, it's pretty uniform. So my question is, if I had a positive charge at point A or B or C, where do you think that positive charge would experience the largest amount of force? And if you had a chance to think about that and answer, you would realize that each of those is going to get the same amount of force because these field lines are parallel. They're the same distance apart. And remember, it's the distance apart that tells us how strong the electric field is. And the strength of the electric field will tell us how much force there is per charge. All right, this is a little video here, and there's a little problem with the video in that when you take video, it takes, 32 frames every second, and I have two Van de Graaff generators here that are going to have opposite charge, and a spark is going to jump between there, and the spark happens in the tiniest fraction of a second. So sometimes the camera caught that spark on film, and other times it didn't. But you'll be able to hear every time it sparks because the sound is captured more continuously. This is a gold leaf electroscope. So if there are charges in here that are in an electric field, those charges are going to experience a force that's going to be away from that. The only place away from that those charges can go is down. So as these charges move down, this gold leaf will stand up because the charges in that metal plate and the charges in there are repelling each other. So again, we're not seeing the spark every single time, but we're hearing the spark. And what's happening is this belt is bringing charges up. There's getting more and more and more charges there. And as there's more and more charges up here, the electric field out here gets stronger and stronger and stronger. So the charges in here get pushed more and more down, and that stands up more and more. The moment all those charges jump across there, the electric field drops to zero, and that falls back down. So this is just in the electric field of those charges that are being generated by that Van de Graaff generator. Let's come back to gravitational fields for a moment, and then we'll compare how different they are from electric fields. But if you were to bore a hole all the way through the center of the Earth, in the exact center there, the gravitational field would be zero. That's because there's just as much mass pulling you to the right as to the left, just as much mass pulling you up as pulling you down, so there's no net force on that person. If you were to move upward, as you move upward, you're getting less mass above you and more mass underneath you. So the field is getting stronger because at the surface, all the mass is underneath you. But if the Earth were hollow, as you moved around there, you're not getting more mass on one side of you. It's all still out there at the rim. So the gravitational field inside there would be zero everywhere. Similarly, if I had this metal sphere and I dump a bunch of electrons on there, those electrons are trying to get away from each other as far as they can. So all of those electrons are going to push themselves off to the surface of that metal sphere, and they're going to equally distribute themselves around that sphere. So if I had a negative charge on the inside, well, it's being repelled by that, it's being repelled by that, it's being repelled in every direction. So in the center, there's no net force on that charge. But I need to try to explain to you why there's also no net force when it's off to the side a little bit. So, well, let's do it this way. Let's say I had a positive charge in here and we had all these electrons distributed around the perimeter. Maybe it's not so hard to see that in the center there, this positive charge is attracted off to here and it's attracted off to here, and there's no net force on that positive charge. But now I want to say, what would happen if that charge was further off to the right? So that's what we're going to do. We're going to move that charge a little further off to the right. Now that charge is closer to this electron, so there's a lot more force. And that positive is closer to here, so again, there's a lot more force. That charge is further away from over here, so there's a lot less force. But even though these forces are smaller, there's more of them pulling off to the left. And even though these forces are stronger, there's fewer of them pulling off to the right. And it does balance everything out so that everywhere on the inside of that sphere, the electric field is zero. And this is coaxial cable. So you're trying to send charges through here to send a signal to your TV from cable or something, if you still have that. But this is braided copper wire, and it forms the shape of a cylinder around that. So what it's doing is it's shielding this wire here from any electric fields. Because if charge builds up on this, that charge is going to evenly distribute itself around the surface area there. And on the inside of that cylinder, there's not going to be any electric field. And that wire there is on the inside of that cylinder. And you don't want an electric field influencing the charges that are moving through there, because that would interrupt the signal. And if like a plane here gets struck by lightning, well, that's a big, large cylinder there. And the electric field on the inside there is going to be zero for the same reasons. The people in there are perfectly safe. Now, let's say we had a very large sphere here and a smaller sphere, and we had the same density of charges. These charges are the same distance apart. So because this is a curved surface, this is pushing this charge that way, this is pushing that charge that way, and so that is a force that has a component to the right and a component down. This is a force that has a component to the right and a component down. The component up and the component down are going to cancel each other out, but both of these have a little bit of a component of force pushing it out. Over here, even though the force was the same, this is on a smaller diameter sphere. So if you take that force and find the component left, and this force and the component left, down and up and down are going to cancel, but both of them have a force with a component pushing it out. And even though the force on this charge is the same as the force on this one, there is a larger force trying to eject that electron off of that surface. So the amount of charge that can be built up onto a surface like that before it gets kicked off, which would be like a spark, is going to be directly proportional to the radius of that sphere. The bigger radius, you can put more charge on there before it kicks it off. So instead of having a round or a spherical surface, we had, let's say this was a cube. And if this is a solid metal cube like this, if there were charges on the inside there and the net and the electric field was not zero, well, the charges on the inside here would experience a force and they would move around until there was no force left on them. So what happens here is the corners of this are going to get more charge. And it comes down to Coulomb's law. Coulomb's constant, charge of one, charge of the other in the separation. Because these charges on the corners are further away, more distance, you need more charge to balance out all the forces. And what this is going to happen is that the points that are further away from the center are going to get more charge put on them. And if this was a teardrop shape here, again, greater distance is going to require more charge. But that little charge there has all these charges be kind of behind it. And that charge is going to very likely get ejected off like that. So here's a teardrop shape and a plate. This might be the charge distribution that is going to be on those surfaces. But very, very strong charge here. And I should say that that positive charge is not going to get ejected off, but it is going to be, because protons don't go places typically, it's the electrons that do, but it could attract negative charges very strongly to that position. And here's a Van de Graaff generator. If you get a chance to play with one of these things, try these two different aspects. Come at it with your finger, and you can get very, very close to this, and it really doesn't hurt because your finger is so pointy, there gets a large charge build up right on your finger, but it's very easy for those electrons to jump to a pointed surface. The voltage on here doesn't have to be that large to be able to jump to a pointed surface. But if you come at it with your forearm, which is a very broad, large radius surface, the voltage on here can build really big, really big, really big. And then finally, it's so big that it can jump to that broad surface in one big wallop. So this would be more like lightning, where lightning is going to just jump to that surface in a really big wallop. And this is like a lightning rod, where the charges jump at a much lower voltage to that more pointy object. In fact, you could kind of make this Van de Graaff generator not wallop any punches, because if you put nails on it, it's going to kick off the electrons from those points just as fast as this belt is putting it on. And that's what a lightning rod does. Lightning rods are these pointy things on the top of a house there. They form two functions. One is to eliminate or reduce the chance of lightning striking that house in the first place. So if a cloud comes over the top here and induces a charge onto the home, if it is a negative charge that's induced into the house and there's these pointy things, well, it's going to kick off that charge at a very steady rate instead of waiting for this big wallop of a punch. If it's positive charges here, it's going to attract negative charges to that spot, but at a much, much lower voltage, because it doesn't have to wait for that big buildup of voltage before it can jump. So two things lightning rods do is they tend to reduce the likelihood of lightning strike by eliminating the charge that gets built up onto the house. The secondary function of a lightning rod is that there's a big heavy cable that is attached to that lightning rod and channeled down into the earth. So that if lightning does strike that rod, it will channel that electricity safely into the earth. And that is all for electric fields.